In topic 2.1, linear motion and force, some of the concepts that we dealt with there were Newton's laws of motion, forces acting on an object, and free body force diagrams. In this bit of work on inclined planes, we're going to make use of those concepts and we'll actually develop them a bit further as well. You can see there the two dot points that we'll be dealing with weight and normal force. So we'll start with weight. Now we have dealt with weight already and you should have a bit of an understanding of what it is, but just want to clarify it considering that it is specifically mentioned in Unit 3. Weight is basically the force due to gravity that acts on a mass. In order to make sense of that, we'd need to refer to Newton's second law. So just writing that brief explanation. And if you recall Newton's second law, that was about an unbalanced force acting on a mass. So from Newton 2, we have F is equal to ma. So those, the force and the mass are both vector quantities. Now if we consider a mass, in this case we'll just draw it as a box, has a mass m, that means that the weight is going to be acting on it in the same direction that the acceleration due to gravity would be acting. So in this case, acceleration due to gravity acting downwards, weight also acting downwards, and you'll notice there that I'm representing that as though it's passing through the centre of mass of the box itself. Now we can therefore consider that the weight of the object is the force due to gravity, so I'll represent that as F with a subscript g, and so the mass of the box is m, and the acceleration that we're dealing with here is the acceleration due to gravity, so that would be the value for g. Now you'll note that this part of the equation, Fg is equal to mg, you can find that in the data booklet. I'm going to use the symbol W for weight, just a little bit quicker and easier, but just keep in mind that weight is equal to the force due to gravity. A couple of extra points to note about this. On Earth's surface, we have a value for g that we use. It's not the value across the surface of the Earth, it's basically the average value. So the acceleration due to gravity does actually vary depending where you are on the Earth, and usually it's going to be fairly close to 9.8, so we're going to always use that value as 9.8 meters per second squared. So that's the also a quantity stated in the data booklet. So 9.8 meters per second squared is the value for the acceleration due to gravity. However, later in this topic, we'll see that that value is not necessarily going to stay the same. It can change, and that the value of g can vary due to a few different factors. The first is that they can vary due to height above the Earth's surface. It can also vary due to which planet you're on. So it could be planet or even moon or even stars. So the value of g, while we do take it to be 9.8 meters per second squared, that value is specific to being on the surface of the Earth. One last point here as well about weight, that sort of tying into those aspects. While your mass is constant, or the mass of any object is constant anywhere in the universe, your weight will actually change. And that will be because of those factors that we've just discussed. Your weight changes due to the gravitational acceleration that you're experiencing. And so that's the brief overview again that we needed to have a look at for weight, and just making sure you're aware of the effects of gravity on weight. From there, we're now going to look at the next idea being the normal force. So this is sort of another subheading. So in order to explain normal force, we first need to go back and look at Newton's third law. And we'll do that by considering two objects that are in contact. So when any two objects are in contact, they're going to exert forces on each other. And that, as I said, is an example of Newton's third law. So for every action, force has an equal and opposite reaction. And it's a critical aspect here to make sense of what a normal force is. So just jotting that down about Newton's third law. And so if we consider that situation, then the normal force itself, you can basically define it as the component of the reaction force. And the component specifically that is perpendicular to the surface. Now, just to make a note here, the word normal, when we use it in a mathematical or a physics context, we actually mean perpendicular. So in saying the normal force, we're saying it's the perpendicular force. The reason why we use the word normal is that it sort of just clarifies specifically that we're dealing with this component that is perpendicular, and so we'll use the term normal quite regularly throughout the rest of this unit. Now, to look at an example and sort of explain this idea a little bit further, we're going to start off first of all with just a box sitting on a table. So here's the table and the box itself sitting on top of that table. So that box is going to have a mass m. We know then that the box is going to exert a force on the table, so we'll label that one Fb, so the force due to the box. And due to Newton's third law, we know that there is an equal and opposite force of the table acting on the box, so that's going to be Ft. Now, if we think about Newton's third law here, there's actually two things to consider. The first is just looking at the box itself. The reason why the box exerts a force is due to its weight. The weight itself is the attraction between the box and the earth. So the action force there is the force of the earth on the box. The reaction force is then the force of the box on the earth. So that's the first application of Newton's third law here. The second application is the one that we're most interested in. That weight force actually corresponds to the force that the box is exerting on the table. So we can say that Fb is actually equal to the weight of the box itself. And we know that that is given by the force due to gravity on the box, and that's equal to the calculation mg. The force of the table on the box then would be considered to be the normal force. So I'm going to represent that with a capital N for normal. You might also see that represented in some sources as Fn, so force that's acting as the normal. Now, to take this a little bit further, first thing, if we only consider the box, or only consider forces acting on the box, what we see is that in the context of Newton's first law, what we can identify is that the box is not moving. The forces therefore must be balanced. So we can say then that the sum of the forces acting on the box, so if we first of all look at the box itself, the box is going to have the weight force acting on it, and it's also going to have the force of the table acting on it, pushing up. So we can say then that Ft plus the weight is equal to 0 because those forces are balanced. We can therefore say that Ft is equal to the negative of the weight. So basically what we're saying there, it's equal in magnitude to the weight but in the opposite direction. But we also know that the force of the table on the box is the normal force, and so we can say that the normal force is equal to the negative weight, so in other words the same magnitude as the weight but in the opposite direction. Second thing to note here is that if a box with greater mass was placed on the table, that means that the weight force will be greater. And you can therefore see that if the weight force is greater, the normal force will also be greater. So you might then sort of think, well, hang on a second, how does the table know that it must exert a greater force on the box? It's not so much that it knows, it's simply just an application of the forces themselves. And the deformation of the table as the box is placed on it means that the table is going to be exerting a force back onto the box, and it's the greater the force that's being applied, the greater the normal force. That then leads us to the next point. If we consider then that a table obviously can't just keep having a greater and greater force on it, it's going to have a maximum force that it can apply. So we could consider it as being the maximum normal force. So that maximum normal force is going to be determined by a few factors. And those factors will be things like what the table's made of. So determined by the materials from which the table's made. So if it was, say, a steel table, might be able to provide more force than a fairly lightweight timber table. So the material is one particular factor. A second and sort of third would be the design of the table. So sort of how far apart the legs are. And so along with that then is the structure of the table. So what sort of reinforcing there is, those sorts of things. Now if the weight force is greater than that, so if the size of the box that's being placed is greater than what the normal force, the maximum normal force that can be provided, that means that the table is going to break. So the normal force is provided by the table, and so the maximum amount of normal force that can be provided will determine the maximum weight that can be supported by the table. Hopefully that gives you a bit more of a sense of some of the ins and outs of normal forces. In the next video we're going to take that a little bit further and look at situations where the surface is no longer horizontal, so we'll start to develop the idea of inclined planes in more detail.